Welcome to this video. In this video we are going to talk about the uniform distribution. Uniform distribution follows a continuous random variable. Assuming the interval lies between a comma b, then the probability density function is f of x is equal to 1 divided by b minus a, upper limit minus lower limit value within this interval a to b, otherwise the value will become 0. Uniform distribution is called as rectangular distribution and it is also known as constant probability distribution. Suppose the uniform distribution f of x is constant in the interval a comma b. Now we consider the limit in x-axis a, this is in x-axis b. The distance between a to b follows the rectangular distribution. In y-axis we have the function f of x. Okay, we know the area of the rectangular is equal to base into height. The total area value is 1, that is b minus a into height is f of x, the total area value is 1, therefore f of x is equal to 1 divided by b minus a. Okay, you get a constant probability distribution. The range varies from a to b, otherwise the value will become 0. Okay, now we have to find the moment generating function and its mean and variance of uniform distribution. Uniform distribution follows the continuous random variable. We know the moment generating function formula for continuous random variable. Another case we can use the moments value, rth moment value or first moment value, second moment value. From this we have to identify the mean and variance value. First we have to derive the moment generating function of uniform distribution. Here x follows the continuous random variable, therefore the corresponding moment generating function is mx of t is equal to f of x into e to the power of tx into dx. Here limit varies from minus infinity to plus infinity, but in our uniform distribution we have the limit varies from a to b. F of x is 1 divided by b minus a into e to the power of tx into dx. Here 1 divided by b minus a is constant, you take outside. Taking integration of e to the power of tx, we get e to the power of tx divided by t. Limit varies from a to b. Now substitute the upper limit minus lower limit value for t, x, e power bt minus e power at divided by t. Okay, therefore the moment generating function is e power bt minus e power at divided by b minus a into t, which is the moment generating function of uniform distribution. Next we have to derive mean by using rth moment value. That is mean is equal to expectation of x, that is mu 1 dash, that is equal to integral x into f of x dx. Here limit varies from minus infinity to plus infinity. According to a uniform distribution, here we have limit varies from a to b. F of x is 1 divided by b minus a into x dx. Okay, 1 divided by b minus a is constant, you take outside. Next, taking integration of x, we get x square by 2. Limit varies from a to b. Now, substitute the upper limit minus lower limit value for x. B square minus a square divided by 2 times of b minus a. B square minus a square can be written as b minus a into b plus a divided by 2 times of b minus a. Now, numerator and denominator 1 b minus a will get cancelled. Therefore, our mean mu 1 dash is equal to a plus b by 2 or b plus a by 2. Similarly, I have to find mu 2 dash by using the e of x square formula. We know the formula for e of x square, that is integral minus infinity to plus infinity x square into f of x dx. In general, we can write like this. According to uniform distribution, the limit varies from a to b. X square into your function is 1 divided by b minus a into f of x. According to the uniform distribution, the limit varies from a to b, x square into 1 divided by b minus a into dx. Now, 1 divided by b minus a is constant, you take outside. Now, a to b x square into dx. Now, taking integration with respect to x, limit varies from a to b, x cube by 3. Substitute the upper limit minus lower limit value for x, b cube minus a cube divided by 3 times of b minus a. This b cube minus a cube can be written as b minus a into b square plus ab plus b square, a square formula, 3 times of b minus a. Now, numerator and denominator b minus a will get cancelled. Finally, we have e of x square is b square plus ab plus a square divided by 3. B square plus ab plus b square divided by 3 is our e of x square. Next, we want to calculate variance value. We know the formula for variance. Mu 2 is equal to e of x square minus e of x the whole square. That is, variance is equal to e of x square minus e of x the whole square. E of x square is b square plus ab plus a square divided by 3 minus e of x the whole square is our mean value, a plus b divided by 2. That is, b square plus ab plus a square divided by 3. Here, a square plus b square plus 2ab divided by 4. Now, you taking the LCM of this, 4 times of b square plus ab plus a square minus 3 times of a square plus b square plus 2ab. Okay, now simplifying this, here we have 4b square, here we have 3 minus 3b square, but totally we have 1b square. Here 4ab minus 6ab. 4ab minus 6ab, take the difference, minus 2ab. Next, 4a square minus 3a square, we get 1a square divided by 12. Okay, which implies a minus b the whole square form or b minus a the whole square form. Okay, which is the variance. Therefore, variance is equal to b minus a the whole square divided by 12. Now, we will discuss some problem based on uniform distribution. Okay, now first problem is, if x is a random variable having the limit minus 2 comma 2, find the probability density function of x and mean variance value. If x is a uniform random variable that has the limit varies from -2 to 2, find the probability density function of x, mean and variance value. Okay, first we have to identify the probability density function of uniform distribution. Here the random variable follows continuous distribution. Since x follows a uniform distribution, then the corresponding probability density function is f of x is equal to 1 divided by second value minus first value, that is b minus a. Here the constant values -2, 2, 2 minus of -2, we get 1 by 4. Limit varies from -2 less than x less than 2. Otherwise the value will become 0, which is the probability density function of given uniform distribution in the interval -2, 2. Next we have to find the mean and variance value. We know the formula for mean under uniform distribution. Mean of uniform distribution is a plus b the whole square divided by 2. Here a equal to -2, b equal to 2. Okay. Mean is take the sum of these two values, we get 0. Mean value mu is 0. And variance, we know the variance formula, a minus b the whole square divided by 12. Okay, now substitute a and b value here. B is 2, minus 2 is plus 2 divided by 12 the whole square, that is 16 by 4 square is 16 by 12, that is 4 by 3. Therefore variance is 4 by 3. Second problem, a passenger arrives at a bus stop at 10 a.m. knowing that the bus will come at some time uniformly distributed between 10 a.m. and 10:30 a.m. Okay, the random variable follows the uniform distribution here and the bus arriving time follows 10 a.m. to 10:30 a.m. So first you have to define the probability density function of the given one. F of x is equal to, okay, the difference between 10 and 10:30 a.m. (0 less than x less than 30), otherwise the function will become 0. Okay, the difference between 10 a.m. to 10:30 a.m. is 30 minutes. Therefore, the function can be written as 1 divided by b minus a is 30 minus 0. We get 1 by 30. Limit varies from 0 to 30. Otherwise, the value will become 0, which is our probability density function of uniform distribution. Next, first question. What is the probability that he will have to wait longer than 10 minutes? Okay, what is the probability that he will have to wait more than 10 minutes? So, we have to calculate the p of x value greater than 10. That is p of x value greater than 10. Greater than 10 means the limit varies from 10 to 30. Minimum limit is 10, upper limit is 30. The function is f of x into dx. That is 10 to 30. Your function is 1 by 30 into dx. Okay, 1 by 30 into integration of dx is x. Substitute the upper limit minus lower limit value, we get 20. Our answer is 2 by 3. Second question. If at 10:15 am the bus has not yet arrived, at 10:15 am the bus not yet arrived, what is the probability that he will have to wait at least 10 additional minutes? Up to 10:15 the bus not yet arrived. Additionally, he have to wait 10 minutes, but totally he have to wait 25 minutes. That is probability of he has to wait 25 minutes. Conditionally, he has waited 10 minutes already. That is P of x greater than 25 minutes. Conditional probability arises here, P of x greater than 10 minutes. Now, by using the memoryless property of exponential distribution, by using the uniform distribution concept here, 15 minutes greater than 25 to 30 f of x dx divided by greater than 15 to 30 f of x dx. That is 25 to 30, integral varies from 25 to 30, f of x is 1 by 30. Next one, 15 to 30, function is 1 by 30 into dx. Okay, 1 by 30 is constant you take outside. For remaining, integration of numerator is 35 minus 25, we get 5. Denominator 1 by 30 is constant you take outside. The remaining difference between 30 and 15 is 15. So totally we have 1 by 3. Okay, that is what is the probability he will have to wait at least additional 10 minutes means the totally the corresponding probability value is 1 by 3. Here the continuous random variable assuming non-negative values is said to have an exponential distribution with parameter lambda, and its probability density function is f of x equal to lambda into e to the power of minus lambda x. A continuous random variable capital X assuming non-negative values, is said to have an exponential distribution with parameter lambda which is greater than 0 if its probability density function is given by f of x is equal to lambda into e to the power of minus lambda x. Here lambda is parameter greater than 0 and the random variable x is greater than or equal to 0. Otherwise the function will become 0, which is the probability density function of exponential distribution. Now we are going to find the moment generating function of exponential distribution. Here the random variable x is continuous, then the corresponding moment generating function is mx of t is equal to integral minus infinity to plus infinity f of x into e to the power of tx into dx. Here under exponential distribution we have the probability density function is lambda into e to the power of minus lambda x into e to the power of tx into dx. Here limit varies from 0 to infinity, greater than or equal to 0, therefore that can be as 0 to infinity. Here lambda is constant you take outside, interval 0 to infinity. Here base is same, add the powers and take the negative value outside. lambda minus t into x dx. Now taking integration with respect to x, e to the power of minus lambda time lambda minus t into x divided by minus of lambda minus t, limit varies from 0 to infinity. Now substitute the upper limit minus lower limit value. Upper limit is infinity. While replacing the upper limit value, we get e power minus infinity. We know the e power minus infinity value, that will become 0. But finally, we have only lower limit value. Minus of lower limit value is minus into minus plus 1 divided by lambda minus t. But that term can be written as 1 minus t by lambda. Now numerator and denominator, lambda will get cancelled. 1 minus t by lambda the whole to the power of minus 1 is our moment generating function. Now expand this term 1 minus t by lambda the whole to the power of minus 1. This is was binomial expansion form. The expansion of 1 minus t by lambda the whole power minus 1 is 1 plus t by lambda plus t by lambda the whole square plus etc. Okay, we know the rth moment value from the moment generating function, that is mu r dash is equal to coefficient of t power r by r factorial in moment generating function representation. Okay, now expand this series according to this factorial form. So multiply and divided by the factorial. First term multiply by 0 factorial by 0 factorial, t by 1 factorial into 1 factorial by lambda plus t square by 2 factorial into 2 factorial by lambda square plus etc. Rth term is t power r by r factorial into r factorial by lambda to the power of r plus etc. Now we collect the t coefficient of t power r by r factorial. The coefficient of t power r by r factorial is r factorial divided by lambda to the power of r, which implies rth moment mu r dash is equal to r factorial divided by lambda to the power of r. From this, we have to identify mean and variance value. Put r equal to 1, we get mean mu 1 dash value. Put r equal to 1 in the above expression, we get mean mu 1 dash is equal to 1 factorial divided by lambda to the power of 1, that is 1 by lambda. Put r equal to 2 in the above expression, we get mu 2 dash, 2 factorial divided by lambda square, that is 2 by lambda square. We know the variance formula. Variance is calculated by mu 2 dash minus mu 1 dash the whole square. Mu 2 dash is 2 by lambda square, mu 1 dash is 1 by lambda the whole square. Okay, take the difference between these two, we get 1 by lambda square. That is the variance value. Mu 2 is equal to 1 by lambda square, mean is equal to 1 by lambda. Memoryless property of exponential distribution. The only continuous distribution having memoryless property. Memoryless property of exponential distribution. Memoryless property of exponential distribution. Here x follows continuous random variable. Follows exponential distribution. Then p of x greater than s plus t, conditional greater than s, that is equal to p of x greater than t, where s and t are the parameters. Okay, which is the statement of memoryless property of exponential distribution. Next we have to prove this statement. First we consider right hand side value, that is p of x greater than t. P of x greater than t. Here the random variable x follows the exponential distribution. Therefore the corresponding probability density function is f of x equal to lambda into e to the power of minus lambda x, where x greater than or equal to 0 and lambda is also greater than 0. So here x greater than t, put t to infinity, f of x into dx. T to infinity, our f of x is lambda into e power minus lambda x into dx. Lambda is constant, you take outside. Now taking integration with respect to x, e power minus lambda x divided by minus lambda, limit varies from t to infinity. While replacing the upper limit value e power minus infinity, we get that value will become 0. Only we have lower limit value t, put x equal to t, lambda into e power minus lambda t divided by minus lambda. This minus into minus plus, lambda will get cancelled. Your final answer is e power minus lambda t, that is equal to p of x value greater than t. Now we consider left hand side value. Left hand side is p of x value greater than s plus t and conditionally x greater than s. Okay, we consider the number line. We mark it as in x axis at x equal to s. Another one, at time exceeds more than s plus t. Okay, this region is the random variable, the time exceeds s plus t. This one, the time exceeds s. Okay, now using the conditional probability formula here, p of a given b, p of a given b can be written as p of a intersection b divided by p of b. Here p of x greater than s plus t and intersection p of x greater than s, whole thing divided by p of x greater than s. Okay, p of x greater than s plus t, this portion greater than s is this portion. Therefore the common term for the above one is p of s plus t divided by p of x greater than s. According to the first equation, p of x greater than t can be written as e power minus lambda t. So here we have, instead of t equal to s plus t, minus lambda times of s plus t divided by e power minus lambda s. Simplifying this, we get the answer e power minus lambda t, that is p of x value greater than t. It's the second equation. Therefore LHS is equal to RHS. Hence we proved the memoryless property of exponential distribution. Okay, now we are going to discuss about the problem based on exponential distribution. The time in hours required to repair a machine is exponentially distributed with parameter lambda equal to half. What is the probability that the repairing time exceeds 2 hours? First subdivision. First we have to identify the lambda value, lambda equal to half. Then the probability density function of exponential distribution is 1 by 2 into e power minus x by 2. Here x greater than or equal to 0. The parameter is lambda, that is equal to 1 by 2. Okay. The first subdivision answer. The probability that the repair time exceeds 2 hours. Exceeds 2 hours means more than 2 hours. The time exceeds more than 2. For p of x value greater than 2. But limit varies from 2 to infinity. F of x equal to dx, that is 1 by 2 into e power minus x by 2 into dx. Okay, 1 by 2 is constant to take outside. Integration of e power minus x by 2 is minus 1 by 2. Limit varies from 2 to infinity. While replacing the upper limit value, that will become 0. Only we have the lower limit value minus into minus plus. Our answer is e power minus 1, that is e power minus 1 answer is 0.3679. Similarly, we are going to solve the second subdivision now. Conditional probability that the repair time takes at least 10 hours given its duration exceeds 9 hours. Okay, it will take at least 10 hours. Already given is 9 hours. Therefore, the corresponding representation is the conditional probability of x greater than 9 plus 1 conditional x greater than 9. Now, by using the memoryless property of exponential distribution, okay, already it takes 9 hours, additionally take 1 more hour. So, that is your p of x greater than 1. Therefore, the limit varies from 1 to infinity f of x dx, that is 1 by 2 into e power minus x by 2 into dx. Okay, taking integration of this one, we get minus e power minus x by 2 divided by minus half. Limit varies from 1 to infinity. Substitute the upper limit minus lower limit value. Upper limit vanishes, only we have lower limit value. Lower limit value is e power minus half. Okay, that is e power minus half, answer is 0.6065. Second problem, the amount of time that a watch will run without having to be reset is a random variable having exponential distribution. Here the random variable is denoted by the letter x. It follows the exponential distribution, and the amount of time that a watch can run without having to be reset with mean lambda, with mean 120 days. We know the mean of exponential distribution, that is 1 by lambda. Mean of exponential distribution is 1 by lambda. Here mean is given, that is 120. 120 is equal to 1 by lambda, which implies lambda equal to 1 by 120. Now we have to find the first subdivision. Find the probability that watch will have to be reset in less than 24 days. Less than 24 days. The watch will have to be reset within below 24 days. That is, limit varies from 0 to 24 f of x dx. That is 0 to 24. F of x is 1 by 120 into e to the power of minus x by 120 into dx. Okay. Now substitute the upper limit minus lower limit value. We get the answer 0.1813. Similarly, we have to solve this second subdivision. Not have to be reset for at least 180 days. For at least 180 days. Already mean is given 120 days. Now we have to find the probability for at least 180 days the watch will not be reset. That is p of x value greater than or equal to 180. Okay, limit varies from 180 to infinity. F of x 1 by 120 e to the power of minus x by 120 into dx. Now taking integration and substitute the upper limit minus lower limit value, we get the answer 0.2231.